Now look at the next question. A block of mass m is equal to 1 kg moving on a horizontal surface with speed vi is equal to 2 meter per second enters a rough patch ranging from x equal to 0.1 meter to x equal to 2.01 meter. The retarding force Fr on the block in this range is inversely proportional to x over this range. That means between this range, that means between x equal to 0.1 meter to x equal to 2.01 meter, the retarding force on the block is inversely proportional to x. That is F is equal to minus k by x. This is the expression for inversely proportional to x. As per this expression, force is inversely proportional to x. X is in the denominator and also it is opposite to the x. Okay. Then for other range, force will be 0. So for x less than 0.1 and for x greater than 2.01, force will be 0 and force will be minus k by x only for this range when the distance x is between 0.1 to 2.01 meter. Okay, then k, the spring constant k is given. This k is given. The value of k is 0.5 joule. What is the final kinetic energy and speed Vf of the block as it crosses this patch? Okay, so here there is a block. So this is the block and the mass of the block is 1 kg. This block is moving on a horizontal surface. So this is the horizontal surface with an initial velocity of 2 meter per second. So initial velocity Vi is 2 meter per second. It enters a rough patch. So this is the rough patch. So it enters a rough patch. As it moves, it enters a rough patch and the width of the patch is this patch extends from x equal to 0.1 to x equal to 2.0. Within this patch, whenever the block moves over or through this rough patch, a restoring force is exerted on that block and that restoring force is equal to minus k by x. Outside this patch, restoring force will be 0. And you are supposed to find out the final kinetic energy and final speed of the block. That means what is the speed of the block as it comes out of this rough patch? What is the kinetic energy, final kinetic energy of this block when it comes out of the patch? So here a variable force is involved because the force is not constant. Here the force is 0, here the force is minus k by x and again here the force is 0. So it's a variable force and we need to apply work energy theorem here. We know that what is work energy theorem? As per work energy theorem, change in kinetic energy is equal to work done. Okay, change in kinetic energy is equal to work done. And we know that change in kinetic energy delta k is equal to integral f dx. And here we will apply the limits xi to xf. So integral f dx. This is the expression of work energy theorem for a variable force. Okay, we had discussed this before. So change in kinetic energy delta k is equal to integral xi to xf f dx equal to integral. What is xi? Xi is the first limit and xf is the second limit. So the patch extends from 0.1 to 2.01. So we are integrating from 0.1 to 2.01 f dx. And within this limit, what is the force? Force is minus k by x. So instead of f, substitute minus k by x dx equal to minus k. It's a constant. We cannot integrate the constant. So take it outside the integral sign. And when you take k minus k outside the integral sign, you are left with 1 by x. And integral of 1 by x dx is log x, ln x. And you will study about integration and differentiation in your mathematics portions. So integral of 1 by x dx is ln x or log x. So we will get minus k ln x and after that apply the limits. What is the limit? 0.1, 2.01. Apply the limit. Then equal to minus k into. After integrating, first apply the upper limit. Then subtract then apply the lower limit. Subtract the lower limit from upper limit. So which is the upper limit? 2.01. So instead of x, substitute 2.01 here. So ln 2.01 minus, then lower limit is 0.1. So for x, substitute 0.1 minus ln 0.1. That is minus k into, you know that log a minus log b is log a by b. So ln 2.01 minus ln 0.1 will be ln 2.01 by 0.1. So minus k ln 2.01 by 0.1 equal to minus k ln 20.1. Okay, 20.1. This is 20.1. And this is the expression for change in kinetic energy. And you know change in kinetic energy is final kinetic energy minus initial kinetic energy. That is Kf minus Ki. That is equal to minus K ln 20.1. It implies Kf is equal to minus K ln 20.1 plus Kf. Sorry, Ki. So bring this minus Ki to RHS part. So it will become plus Ki. So you will get Ki minus K ln 20.1. That is final kinetic energy Kf is equal to half mvi square. Kinetic energy is, initial kinetic energy is half mvi square minus K ln 20.1 equal to half into 1 into. What is initial velocity? Initial velocity is given in the question. It is 2. So vi square will be 4. So half mvi square is half into mass is 1 kg into 4 minus k. The value of k is given in the question. It is 0.5 into ln 20.1. Then from this kf is equal to, here 2 and 4 will cancel. You will get 2 here. So 2 minus 0.5 ln 20.1 equal to, take the logarithm table and find out the value of 20.1 from the logarithm table. You will get the value and multiply that value with 0.5. You will get 1.5 as the answer. So 2 minus 1.5 is equal to 0.5 joule. So this is the final kinetic energy. So one part of the question is over. We had calculated the final kinetic energy of the object. Then we need to find out the final velocity also. So final kinetic energy is Kf and it is half mvf square. So we calculated half mvf square equal to, and that is 0.5. So the final kinetic energy is 0.5 and we know that final kinetic energy is half mvf square, that is 0.5. So therefore vf square is equal to 0.5 into 2 divided by m equal to 0.5 into 2 is 1 and mass is also 1 kg. 1 by 1 is 1 meter per second is the final velocity. Okay children, so this is the final kinetic energy and this is the final velocity of that block. And this is the basic principle that we are using here. Kinetic energy, change in kinetic energy is equal to work done. And this is the expression for variable force. And integration will be a little bit difficult to understand because you have not studied integration till. And unfortunately or fortunately you are studying integration in your class 12 mathematics. So it's better you can by heart this step, or you can by heart the result of integration. Integral of 1 by x between the limits 0.1 to 2.01 is log 2.01 by 0.1. Okay children. Now we can discuss the next question. That is, this is the next question. A 2 kilogram body moving on a level surface collides and compresses horizontal spring of force constant K is equal to 2 Newton per meter through 2 meter. The coefficient of kinetic friction between the body and the surface is 0.25. Calculate the velocity of the body while colliding. So there is a 2 kg body. It is moving on a level surface. It collides and compresses the horizontal spring. So this is the spring. This body moves and compresses this spring. Force constant of that spring is given 2 Newton per meter. And compression takes place through 2 meter. the coefficient of kinetic friction between the body and the surface. That means this body is moving on a level surface, isn't it? So the coefficient of friction between the body and this surface is 0.25. Calculate the velocity of the body while colliding. So what is the velocity of the body during collision? Here we can consider before collision. What happens? Before collision, our spring is at rest, but body is moving towards the spring. So body is moving, spring is at rest. But after collision, what happens? Once the body collides with the spring, body comes to rest and the spring compresses. Okay, so after collision, body comes to rest and the spring compresses. So what happened? That is, the kinetic energy, when the body is in motion, it will possess some kinetic energy. The moment it collides with the spring, it comes to rest. So the kinetic energy of the body is converted to the potential energy of the spring, and also in one more thing, to overcome the frictional force between the object or between the body and the surface. So the kinetic energy of the body is spent in compressing the spring, and also some amount of kinetic energy is spent to overcome the frictional force. And you know the kinetic energy of the body is half mv square, and the frictional force expression is mu into n, where mu is the coefficient of friction and n is the normal reaction. And normal reaction is balanced by weight of the body, that is mg. So n can be considered as mg. So the frictional force is equal to mu n equal to mu into mg. And work done to overcome the friction, that means work done by the frictional force, as frictional force into displacement. So frictional force is mu mg into displacement. That is the work done to overcome the friction. And what is the work done to compress the spring? So work done to compress the spring is the potential energy of the spring itself, and that is equal to half k x square or half k d square, where d is the displacement here. So we can write kinetic energy of the body is done or is partly used to compress the spring, and it is partly used to overcome the frictional force. So kinetic energy of the body is equal to work done to compress the spring plus work done to overcome the friction. And what is the expression for kinetic energy? It is half mv square. So equal to half into mass is 2, and v square we don't know, we need to find out this velocity, equal to kinetic energy of the spring is work done to compress the spring is half k d square. So half into the value of k is given in the question, it is 2 into, and displacement or the distance through which compression has occurred is also given in the question, it is also 2. So d square will be 2 square. Then plus work done to overcome the friction is mu mg into d. Coefficient of friction is given, that is 0.25 into mass is 2 into g is 9.8 into displacement d is 2, again 2. And here this 2 and this 2 will cancel, and we are left with 4. 4 plus 0.25 into 4. 2 into 2 is 4. 4 into 0.25 is 1. And 1 into 9.8 is 9.8. So v square is equal to 4 plus 9.8. Therefore v is equal to square root of this sum, and that is equal to 3.74 meter per second. So this is the velocity of the body during collision. Okay, so here we need to apply this basic principle, that is kinetic energy of the body is equal to work done to compress the spring and work done to overcome the frictional force. So with this, the numericals part is over. So with this I am concluding this session. Also I am concluding this whole chapter, work, energy and power. And notes of the topic have been uploaded. No YouTube video will be uploaded based on this topic because it's a numerical part. And we will meet in the next session. Till then, take care all of you. Stay home, stay safe. So throughout this video lesson, you can pause the video and note down the questions, and that is the proper way. Otherwise, the images of these questions will be uploaded in the Google Classroom. So soon after the session, you can download it and note down into your notebook. Okay. So all of you take care. Stay home, stay safe, keep learning. Thank you.